Okay, if you are watching this, you have survived Chapter 1 test. So, here we go at Chapter 2. Chapter 2 is history of the periodic table. We've got atoms. We've got it all. We've got, let me zoom in a little bit more so you can read this just a little bit better. There we go. History, atoms, molecules, ions, isotopes, all that good stuff. I might split this in half actually. So this might just be part 1 of the notes. So let's talk about first fundamental chemical laws. So there are some fundamental chemical laws that you've got to know in chemistry. And I'm trying to write as legible as I can while still going quickly. So fundamental chemical laws would be, the first one, you could probably guess, the law of conservation of matter. The law of conservation of matter. And you guys know what this is. This states that matter cannot be created or destroyed. So matter, making sure I'm on the screen. Yep, we're good. Cannot be created or destroyed. This means if I start out with 12 molecules of something on the left side of an equation, I end up with 12 molecules of something on the right side of the equation. You will probably have to draw something like that on the AP test. There's always some kind of particulate drawing, just like we were doing with the change cards on Friday. And you have to count the particles and make sure you end up with the same amount of particles on the other side. Easy point, but something still to watch out for. The law of definite composition. This might be new to you, CP Chemers. This says that two chemicals, a lot of the times two elements, combine always. So you can underline the word always in equal mass proportions. They combine always in equal mass proportions. What do I mean by that? Well, this means if I take sodium, which if you look at the periodic table is 22.9 grams in 1 mole of sodium. So the molar mass in the periodic table is the same as the number of grams in a mole. And I add chlorine to it. That's always going to combine with 35.4 grams of chlorine. But if I take hydrogen and I combine it with hydrogen, which is, we'll just talk. If I combine hydrogen and oxygen, and if I have 16 grams of oxygen, I know I have to have 2 grams of hydrogen because oxygen is about 16 grams, it's 15.999, and I know I need 2 hydrogen for every 1 oxygen. Hydrogen has a molar mass of 1, but I need 2 of those to make H2O. Then there's also the law of multiple proportions. Very similar, but the law of multiple proportions, similar to what we were just talking about. This is actually looking pretty decent on the screen. I'm pretty happy with that. The law of multiple proportions is basically saying it's always the same thing or the same proportion under different conditions. So whatever I start out with, I have to keep that proportion. For example, if I have copper, which is a molar mass approximately of 63.5 grams, and I'm combining that with chlorine, which is a mass of 35.4 grams. If that's one situation. If my next situation has copper with 127 grams, I have now multiplied this copper by 2. If I'm multiplying that copper by 2, I also have to multiply my chlorine by 2. So now my chlorine has to be 70.8 grams. So I'm keeping my proportions the same. My composition staying the same, my proportion stays the same. It's kind of the same thing, both, but I just wanted to write that out there. So, last thing I want to say about that is if one mass is equal, the other must, underline the word must, be a simple whole number ratio. So it's always going to be a simple whole number ratio. And I think you have problems like this in the book you're going to be working out. And you'll see what more like what that means when you do a couple practice problems. So this next part you must memorize. This is on the test. You have to know these next 4 things, which are Dalton's atomic theory. It's all stuff that you mostly already know, but I just want to put it out there, and you got to remember all 4 of these things. You have to memorize these. Number 1, all matter is made of tiny, indivisible particles called atoms. So, number 1, everything's made of particles. Number 2, this sounds basic, but it's true. Atoms, and we know we can split an atom now, but this is back to Dalton. So back in his time, thought they were indivisible, but you still need to know this. Atoms, this is pretty deep, guys. Atoms of one element, get ready for this, are the same. What? Atoms of another element, wait for it, are different. Atoms of one element are the same, atoms of another element are different. So, number 1, everything's made of particles. Number 2, atoms of one element are the same, atoms of another element are different. Number 3, we've already talked about this, but once again, now we're talking about compounds. Compounds form in simple whole number ratios, and for reactions are just a rearrangement of atoms. Reactions are a rearrangement of atoms. So I want you to memorize that. I want you to know all those parts of Dalton's atomic theory. And Dalton's like, well, everything's made of particles that are indivisible. Until we came to J.J. Thomson. And J.J. Thomson was basically said, oh, no, you didn't? Wow, that's an N. Wow. I'm going to have to read that. That looks so bad. Oh, no, you didn't, all right? Because J.J. Thomson did this cathode ray tube experiment. So I'm going to try to draw this out, pretty basic. So a cathode ray tube has 2 sides. So I'm going to try to draw this out. Go like here, this little part in the middle. All right, this is a cathode ray tube. Pretty basic. You can Google this if you want to, see what it actually looks like. But the cathode ray tube has a cathode with a positive side and an anode with a negative side. And he was shooting through here, all right, charge. So he's shooting charge here. Shooting charge here. But what he did is he put a magnet up against here. And the magnet had a negative side and a positive side. Negative side and a positive side. And as he was shooting this positive charge through here, shooting these charges through here, he saw that when you put a magnet up next to it, it was pulling the stream towards it on the negative side, but pushing it away on the opposite side. So he knew that there had to be something here. Actually, I think this side was pulling it towards. The positive side was pulling it towards, and the negative side was pushing it away. Whoops. Because J.J. Thompson, this was actually a negative charge he was shooting through here, this current, he actually discovered the electron. So J.J. Thompson discovered the electron. So now there's smaller parts of the atom. So J.J. Thompson discovered the electron with the cathode ray tube. Another model was plum pudding. So plum pudding is an English like cake type thing. There's like cherries and plums all through it. And plum pudding was just saying that there's positive, negative charges all randomly distributed out through basically a sphere. And in this model, it was saying that atoms are divisible, but after they're divided, atoms are divisible, but no longer identifiable. So you could split an atom, but you could no longer tell what it was. Then came Ernest Rutherford. So Ernest Rutherford, or Rutherford, I say Rutherford. He did a pretty cool experiment as well. And this should sound familiar to our CP chemers too. So Ernest Rutherford shot a positive charge. So he shot alpha particles, this is like alpha gun. All right, an alpha particle, I'm going to show you what it is. An alpha particle is basically 4,2 He. So if you're looking at the periodic table, 4 is the atomic mass, 2 is the atomic number for helium, and this is basically just a massive positive particle. So he was shooting these alpha particles. Ooh, we gotta stay on the screen. He was shooting these alpha particles out of here, out of this gun. Positive, 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 into a really, really, really thin piece of gold foil. And gold foil can be worked really, really thin. People that had me freshman year, or I think even CP Chem watched a movie where they beat gold foil really thin because it's super, super malleable. And if you had, for example, a Bible of all gold foil pages, it would be the thickness of one sheet of paper. So gold foil is super, super thin. So Ernest Rutherford was trying to get to an atomic level, which he didn't, but he was close. And on the back side of this experiment, he put a phosphorus screen, because he knew that these alpha particles hitting this screen should light up. And what he expected them to do as they went through this gold foil was go straight through. That's what he expected. But they didn't. These massively positive particles were bouncing this way, and bouncing this way, and bouncing this way, and bouncing this way. And what he discovered is that these positive particles, there was some massive positive place in the atom that these particles were reflecting off of, because we know that like charges repel. And what he discovered here was, well, his conclusion, Ernest Rutherford said, because a lot of them did go straight through. What he wasn't expecting was for them to some come back and some bounce off. His conclusion was the atom is mostly empty space. The atom is mostly empty space. Comma, with an extremely dense positive center. And you guys can imagine that this dense positive center was the nucleus. So Ernest Rutherford discovered the nucleus because the nucleus has protons and neutrons. Neutrons have no charge. Protons have a positive charge. So what he discovered was the nucleus. So up here, J.J. Thompson is shooting electricity through, and this electricity was attracted to the positive side and reflected from the negative side, so he discovered the electron. Ernest Rutherford discovered the nucleus. The Bohr model. So Niels Bohr came up with the Bohr model, which is most similar to the solar system. So it's rings of electrons. So you've got your nucleus, your positive protons, your neutrons in the middle, and then you have your rings of the electrons. Here's an electron, E negative. I do E negatives flowing all around. And in this model, the first ring could hold 2, the second ring could hold 8 electrons, third 8, fourth 2. That's what you learned freshman year, 2882. And those rings are also called an orbital. And an orbital is defined as where an electron is most likely. So underline most likely, because it's really, really difficult to find the actual location of an electron, where an electron is most likely to be found. It's actually really, really difficult to find the exact location of an electron. Really difficult to find the actual location of an electron. So, you guys can pause if you need to copy that down, but I'm going to keep moving. So, it's so hard to find the location of an electron. All right, there was this guy named Heisenberg who came up with the Heisenberg uncertainty principle. The Heisenberg uncertainty principle. And this is just a quick overview of some history stuff. So, for this, what I want you to do is close your eyes. Kind of weird because you're probably by yourself somewhere. And envision yourself in a pitch dark room, like almost like one of those like walk-in like freezers or refrigerators that you'd see in like a big restaurant. It's not cold, it's not freezing though, okay? So you close your eyes, you envision yourself in this dark room that's closed in on 4 walls. Hopefully you're not claustrophobic. And in this dark room, I want you to envision a helium balloon floating in the middle of the room. Pitch black, you can't see anything. There's a helium balloon not floating at the ceiling, not on the floor, but in the middle. And what I would want you to do would be tell me the location of that balloon. So with your eyes closed, what would you have to do to tell me that location of the balloon? Giving you some time to think. So here's the empty room. Here's the balloon in the middle of the room. In order for you to find that balloon, you're gonna have to walk towards the balloon and like have your arms out, like trying to feel your way of like what's there. Those are your arms. Really good drawing. Here's the problem. In the pitch dark room, as soon as you touch the balloon, you've also changed its location. So you couldn't tell me the exact location of the balloon because I want to know where the balloon was in the room before you touched it. That's the same problem with an electron. And this is how he kind of created his Heisenberg uncertainty principle, which said, you never know the exact location of an electron. Because if you shoot energy at it, because electrons are so light, as soon as you do that, you'll move the electron, and electrons are always also moving, so you just never know the exact location of an electron. So hopefully that made sense. Might be kind of weird. If you have more questions on that, we can ask me at school. So if I see 12.6C, this is also some really basic review, but just to make sure you guys know, 12 is the mass number of carbon, and the mass number tells me the number of protons plus the number of neutrons. So 12 is the mass number. You'll find that below carbon on the periodic table. Number of protons, number of neutrons. 6 is the atomic number, which is the identity of the element, which is the number of protons or the number of electrons in its neutral state. So 6, if I have 6, which is the upper right-hand corner of carbon on the periodic table, number of protons or the number of electrons. So to figure out the number of neutrons, I'm obviously going to take the mass number minus the atomic number to get the number of neutrons, because I have protons plus neutrons. Subtract the number of protons, that leaves me the number of neutrons. Atomic mass, the way this is figured out, atomic mass, we're going to do an activity with this, I think later this week, is the weighted average of all isotopes of an element, which maybe would lead you to a question. The atomic mass is the weighted average of all isotopes of an element, which might lead you to ask, what is an isotope? An isotope is an element or atom with the same number of protons, comma, but a different number of neutrons. I'm doing N0 for neutrons. In other words, a different mass. Different mass. So, different isotopes of carbon would include something like carbon-13 or carbon-14. These are radioactive forms. I'll just write it down. These are radioactive isotopes of carbon, mostly used for carbon dating. So to tell how old something is, you'll use carbon-13 or carbon-14. Carbon-14. When am I going to talk about mass spectroscopy? That's a good question. I'm going to give you this definition, and then I'm going to show you more about it in class. So mass spectroscopy, spectrometry is based off of a mass spectrometer, which is a machine where you shoot ions in and you see how like a magnet or something bends them. So mass spectrometry is to tell me all the different isotopes of something, and it basically gives you this equation. I'll show you this in class. Is the average atomic mass is equal to the mass of isotope 1 times its percent abundance in nature. The mass of isotope 1 times its percent abundance plus the mass of isotope 2 times its percent abundance, and it would be and so on and so forth. However many isotopes they are times their percent abundance, that is how you get the average atomic mass, and that's determined through mass spectrometry, which I'm going to show you on this week in person. It's not great on notes. So that is the basics of the history of the periodic table. How long have we been going? I'm not sure. I'm going to stop that one, and I will do part 2, which is going to be the basics of periodic table and naming compounds as a second part. I think that'll make the most sense.